Natural world of minerals shows endless diversity of characteristics which help their identification and ability to distinguish one from the other. Mineral identification is not only of interest to enthusiasts in the habit of collecting minerals and rocks specimens for their personal collection, but of paramount importance to students of geology, and more so when they become professionals. As microscopic and other high-tech identification of minerals may be time consuming and not always available at will, one has to depend on one's ability to read a mineral of its various properties that depend upon our physical senses like vision, our ability to distinguish various forms, shapes, weights, feel, taste, touch, and many other properties. In mineral world, such an attempt is referred to as physical properties of minerals. In this lesson on megascopic identification of minerals, we shall consider the following aspects: characters depending upon light, characters depending upon state of aggregation, character depending upon senses, and characters depending upon heat, magnetism, and electricity, including radioactivity. Minerals in natural form may be transparent like a thin sheet of muscovite, and the opposite of it is opaque like galena, pyrite, and hematite. Between these two there may be a subtransparent and translucent variety depending upon how much light could pass through them. Next to transparency, the first thing that our eyes will notice is its color. Thus, color is an important property for identifying minerals. Commonest mineral, quartz, is the best example. Color given by powder of the mineral is known as the property streak. White or colorless mineral will give white streak, but dark colored minerals may give a different color streak or the same colored streak. One has to remember that mineral harder than the streak plate won't yield any powder while scratched on it, but instead scratch the streak plate and produce white powder from it. Some minerals like labradorite show a succession of colors like in a rainbow while the mineral is turned in sunlight. The phenomena is called play of color. The next important property called lustre refers to the nature and quality of the reflection it produces. Different names given to lustre are our attempts to compare reflected appearance to things we are familiar with. Broadly, lustre is termed metallic when it is appearing like a metal like native gold, silver, copper, chromite. Galena have metallic lustre. Lustre not resembling metals are said to be non-metallic lustres. If they are like glass, it is termed vitreous like that of quartz and topaz. It is called resinous when it is like resin, as in sphalerite. Pearly if like mother of pearl, for example talc. Silky when it resembles lustre of silk or rayon, as in asbestos or satin spar variety of gypsum. Lustre of chalk or clay is naturally called dull. On the contrary, brilliant glossy lustre of a diamond is called adamantine. The prefix sub is used when comparison is not so perfect like submetallic, subvitreous, subresinous. Submetallic lustre is intermediate between metallic and non-metallic lustres and typically exemplified by the mineral wolframite. Another way of considering lustre is by its degree. The term splendent is used when the mineral has glossy brilliance like that of a diamond. When it has sparkling brightness, it is said to be glistening. Shining is just bright by reflected light, and earthy when it has dull luster of soil. It goes without saying that for determining luster or any other physical property, the mineral has to be non-weathered and should present as far as possible freshly broken surface. Lastly, a property as a result of mineral surface excited by ultraviolet light is very distinctive for some minerals for identification. It is called photoluminescence, but it is visible under total darkness. If the mineral is luminous only during the period of exposure to the ultraviolet rays or other stimulus, it is called fluorescence. Scheelite showing yellowish green and scapolite showing yellowish orange sheen in ultraviolet light are the best example of fluorescence. Diamond and ruby exhibit phosphorescence under X-rays. These two properties are widely used in mineral prospecting as for picking diamonds from crushed and washed kimberlite. In this module, we will consider form and habit and cleavage and fracture. Under form, we ascertain whether the mineral is crystallized or non-crystallized. Quartz and calcite present well-developed museum specimens showing pronounced crystal faces. Cryptocrystalline term is used when the minerals show only feeble development of faces. Total absence of crystalline nature makes a mineral amorphous, as in the case of natural glass called obsidian. Development of individual crystals and aggregate tend to present a characteristic pattern shape in totality. This is known as habit of a mineral. Different habits are assigned to individual crystals of aggregates. Thus, acicular, which is like needles, bladed like a knife blade, fibrous like hair threads are a few habits of individual crystals. For crystal aggregates, terms such as amygdaloidal, that is almond shaped, botryoidal like bunch of grapes, oolitic small spheroids, ellipsoids resembling fish eggs, columnar like columns of a building are used. Cleavage is one of the most important property to distinguish minerals and is the tendency to split apart along planes of weakness, which is known as cleavage. A mineral may have 1 like in mica, 2 like in pyroxenes and amphiboles, 3 like in galena and calcite, 4 in case of fluorite, or even in 6 directions like in mineral sphalerite. On the basis of quality of development, terms like perfect, good, imperfect, poor or absent might be used. Calcite, muscovite for example have perfect cleavages, diopside has good while pyrite has poor. The other way to describe cleavage is in relation to crystallographic orientation of a mineral. Calcite on the other hand has 3 perfect cleavages parallel to 3 rhombohedral faces. Muscovite has perfect basal cleavage parallel to basal pinacoid. Fluorite is said to have octahedral cleavage as it has 4 cleavages parallel to octahedral faces. A mineral like calcite with 3 perfect weak planes when struck with a hammer will crumble, producing several smaller rhombs of crystals exactly like the original. because planes of weakness are parallel to the three rhombic faces, or a bigger cube of galena into smaller galena cubes for the same reason. A similar tendency in minerals and rocks to break along some planes other than cleavages is called parting or false cleavage. Parting is unrelated to crystal symmetry of faces, but results due to twinning, deformation, exsolution lamellae, or oriented inclusions of other minerals. There is yet another linear characteristic in some minerals called striations. This is commonly seen in minerals like quartz, tourmaline, and pyrite as parallel lines or furrows just on the surface and not within the crystal. Thus, striations are not the planes of weakness as cleavages are. The term even is used when the surface is flattish like in mineral magnesite. When fibers and splinters are revealed along the fracture surface like in asbestos, it is called fibrous or splintery. When the broken surface is marked by rough jagged edges as in broken cast iron or native copper, the fracture produced is called hackle. Mineral kyanite broken along the length will show hackle fracture. A broken surface produced by a clay lump or chalk will naturally be called adi. A clear understanding of the term cleavage and fracture should be grasped early and permanently. Point to remember is that there is no question of fracture for minerals with perfect cleavage, as fracture becomes important only when cleavage is poor or absent. Minerals muscovite and quartz are two extreme examples. Muscovite has perfect cleavage, quartz has none. Thus, cleavage becomes most important in muscovite and fracture in quartz. Two of the most characteristic features under this category are specific gravity and hardness of minerals. Specific gravity, that is the weight of a mineral divided by the weight of an equal volume of water, is called relative density. Color and some other properties of a mineral may vary considerably, but specific gravity is more or less constant and depends upon the weight of the constituent elements and the nature of their packing. Graphite and diamond, both of which are pure carbon, exemplify the latter. Loosely packed graphite has a lower specific gravity, just 2.3, while tightly packed diamond has 2.54. The effect of constituents is far more apparent. Two sulfides, that is galena lead sulfide and sphalerite zinc sulfide, present a good example. Galena has far more higher specific gravity of 7.5 compared to sphalerite, which has only 4. Other examples include anhydrite 2.93 and barite 4.5. Native gold is one of the highest specific gravity, which is between 15 and 19, while opal is one of the lightest, just 2.1. There are a number of methods available for determining specific gravity of minerals in laboratory. Due to lack of space and time, these will not be discussed here, but Walker Steelyard balance is one of the easier techniques to determine specific gravity of fixed size minerals. Since average density of crystal rocks is between 2.54 to 2.75, and because quartz, the commonest mineral of the earth crust, is also around 2.65, this figure should be mentally recorded and our hands accustomed to recognize it by experience. Specific gravity of minerals which will have specific gravity similar to this figure, that is between 2.65 to 2.75, can be called medium those above 3 having high and those below 2.65 as having low specific gravity. As a generalization, silicates and carbonates will have somewhat lower specific gravities between 2.5 and 3.5 as compared to metallic minerals which will have between 5 and above. Hardness of minerals is an extremely useful property for their identification and is the resistance that it offers to scratching. It depends upon atomic structure and the density of packing of its constituent ions. If one can scratch a mineral like talc with fingernail, talc is naturally softer than fingernail, but the same attempt with fluorite or quartz will be futile and it will surely hurt the fingernail. Thus, quartz and fluorite are harder than fingernail. This is the working principle for assigning and determining relative hardness in minerals. Geological world will be indebted to Carl Friedrich Moh, a German geologist, for developing a simple device for determining relative hardness of minerals, what now is known as the hardness box, comprising 10 minerals with increasing hardness: talc 1, gypsum 2, calcite 3, fluorite 4, apatite 5, orthoclase 6, quartz 7, topaz 8, corundum 9 and diamond 10. The relationship of hardness above is not quantitative only, but relative. Gypsum is not 2 times harder than talc, nor is diamond 10 times. Hardness box also comes in the form of a pencil box, where these minerals are fixed at the tip of pencils. For determining hardness, a fresh surface of a mineral is scratched by the minerals in the hardness box. If the unknown mineral is scratched by, say, orthoclase, which is having a hardness of 6, but the mineral apatite itself gets scratched by it, the hardness of the unknown mineral can be taken as 5.5. In the absence of a hardness box, it is still possible to test the hardness of a mineral by using some of the household items like fingernail having a hardness of 2.5, copper coin about 3, glass 5.5 to 5, knife edge 5.5 to 6, steel file 6.5 to 7. It is always useful to group minerals of more or less similar hardness in your mind. There is yet another characteristic under this category called tenacity and refers to the resistance that it offers to breaking, tearing, bending and crushing. A mineral is called brittle when it can be broken or powdered easily. Both tough like galena and fragile like sulfur will come under this category. When a mineral on bending will return to its position are called elastic like mica. Talc on the other hand is flexible, though bends, but does not come back to its original shape with pressure removed. Sectile minerals like selenite, gypsum and talc could be cut with a knife to produce shavings. Minerals that could be hammered into thin sheets are called malleable. Native minerals like gold and copper are good examples. Minerals could also be drawn into wires and are referred to as ductile. The way various constituents are joined together to form a mineral and the fact that constituent elements and compounds have different physical and chemical properties, the final product, the minerals may react differently to our senses. Feel, odor and taste also have their say in mineral identification, at least for few of them. In feel, we shall see that handling of a mineral will immediately convey to our mind whether the feeling is soapy, greasy, smooth or rough. As a test, handle minerals talc and chromite individually. After some time, close your eyes and handle them again unknowingly. You will never make a mistake in identifying them with your eyes closed. Talc will be soapy while chromite will be rough. Graphite is not only greasy, but it will also soil your fingers. So will mineral pyrolusite. Certain minerals impart cooling effect when touched. Marble, that is calcite, is one. So is diamond on account of it being a good conductor of heat. In fact, gem experts use this property in diamond identification. Coming to odor, minerals when rubbed, struck, breathed upon, heated or treated with some solvents or simply smelled can give some distinctive odors which helps in their identification. Commonly recognized odors are the following: garlic smell from arsenic compounds, arsenopyrite upon heating or grinding, mushy smell, clay minerals when breathed upon, fetid that of rotten eggs is sphalerite when scratched producing H2S, taste. Though not a very healthy practice, but certain minerals due to their soluble contents do provide some peculiar taste that can be used in identifying them. Salty halite, which is sodium chloride, alkaline, sodium potassium minerals, astringent or puckering, alums, green vitriol, hydrated iron sulfate, bitter, which is Epsom salt, which is hydrated magnesium sulfate. Thermal properties of minerals is a vast field. However, on a routine basis, these are hardly used for macroscopic mineral identification. At this stage, it is sufficient to know that different minerals, when subjected to heat at atmospheric pressure, have different fusibility. That is, the temperature at which a mineral melts. It may begin with partial loss of water and other gaseous components, may involve polymorphic inversions, and finally, it may produce partial or total melt. This feature was earlier very popularly used in blowpipe analysis for minerals identification. It is sufficient to know that temperature of fusion for different minerals is different. Some of the common minerals with their approximate temperature of fusion are in descending order as follows: zircon at 2500 degrees centigrade, olivine 1400 degrees centigrade, plagioclase 1300, garnet 1050, natrolite 965, quartz at 573. Coming to magnetism, here we are interested in the magnetic property of minerals that can be detected by a simple horseshoe or a bar magnet. There are only two minerals which are strongly magnetic: magnetite and native iron. Pyrrhotite are weakly magnetic. Other minerals can be considered non-magnetic for practical purposes. However, a large number of minerals under stronger electromagnetic field can display different degrees of magnetism. In fact, this becomes the very basis for magnetic separation of minerals, both on laboratory scale and for ore dressing plants. Under an electromagnetic field, ilmenite, wolframite, siderite, almandine, hematite and chromite turn moderately magnetic, while tourmaline, spinel, monazite are weakly magnetic, but minerals like quartz, Feldspar, calcite, corundum, cassiterite and sphalerite are still non-magnetic. Electrical properties are hardly ever used for megascopic identification of minerals, but are nevertheless interesting and useful, depending upon their capacity for conducting electricity. Minerals can be divided into conductors, non-conductors and semiconductors. Native minerals like copper, silver, gold and metals sulfides are conductors. Majority of minerals come under the category of non-conductors. In a few of them, it is possible to develop electric charge by using stress. If heat is the source of stress, the effect is called pyroelectricity. If the source happens to be pressure, the phenomena is termed piezoelectricity. Tourmaline is an example of pyroelectric mineral. When heated, a tourmaline crystal develops positive charges at the base of the crystal, while it becomes negatively charged at the upper surface, which is relatively sharper end. Topaz also exhibits this phenomena to a lesser degree. The developed charges are measurable in terms of charge per unit area. Piezoelectricity has far more application in science and industry. This property was first time detected in 1881 by Pierre and Jacques Curie, when they found that quartz crystals subjected to properly directed pressure develops positive and negative charges at opposite ends. Natural radioactivity in minerals and rocks is related to the presence of uranium U-238 and U-235, thorium that is 232 and other radioactive elements like potassium K40 and rubidium. These unstable nuclei of uranium, thorium, potassium and rubidium decay non-stop at constant rate to their stable products by emitting alpha, beta particles and gamma radiations. Various radiometric counters like Geiger-Müller counters, scintillation counters and radon detectors are in use for detecting radiometric minerals and rocks in the field. To summarize, we can say that to identify minerals, we can use a number of things like our vision, our feel, our ability to distinguish colors, their hardness, their cleavage, their fracture and so many things which come in various shapes and forms. To end this lecture, we can say that all that glitters is not always gold. Thank you.